Welcome back everybody to mass spectrometry. We did a few functional groups to see how the molecules break up in a mass spec machine, and we can take the masses that are given out by the detector and match them to fragments, and then we can put them all together and then conclude the structure or the identity of the molecule in a lot of cases. All right, so here we're given the molecule because we want to talk about what could happen if there is an alkene or any other functional group, and what are the typical pathways. All right, here's a branched alkene. Let's see what can happen. So as we said, the lone pairs are really vulnerable, and the pi bond electrons are also vulnerable to attack, because when it goes through the machine, it's just hit by these high energy electrons, and they can knock off electrons from the molecule. And here, the two electrons that are most vulnerable are the pi electrons. And so you can take this and you can see how one of them can be taken out by the machine. All right, so here if you take this out, let's say you can take this one out, it doesn't really matter, but if you take that out, we can have, well, there are two possibilities. You can take this one out or this one out. Let's say we take this one out. So an electron at high energy bombards with it, and you eject an electron from the molecule. Then you would get a molecule that has an unpaired electron, which means there's a hole here, which means that's a positive. So here's your radical cation. All right, you could, as we saw before, also write this is the exact same thing as this. Well, once you take off an electron, you destroy its stability in some sense, and this is very, very high energy. It's going to unravel. The unraveling takes place, starting at the place of the electron impingement on this molecule, which creates that positive hole. So here's your positive, here's a radical. What could happen with this? You could think of this as having a methyl group here, an ethyl group here, and all these are now vulnerable. Let's look at this, 98 and 83. So 98 we're going to 83 is a 15, and 15 typically means methyl, and we saw that before. All right, so here you can see there is a CH3. Okay, so alpha to that, you can see that's a CH3. That can then go away as a radical, and you can have a methyl missing from the original molecule, and that would make its mass become 83. Okay, so here's your mass of 83 for this molecule, and the charge is 1, so that's m over z 83. All right, what are the other possibilities? How could you get 69? If you take 83 minus 69, that's 14. So you have to have a CH2 being ejected. The most probable case is 98 going to 69 with minus 29. So that's going to be an ethyl. So an ethyl, again, you can see from here, there is this ethyl group here which can leave. Same here. So let's write that down. And I'm going to write this as an A and this as a B. And let's see what happens at B. Let's look at your B pathway, which is basically the same radical cation. You can either do the positive here or here, but in this case, you are going to have to take off an ethyl. So the ethyl can fragment away, and these two electrons can be homolytically cleaved. So, and we saw that we can have homolytic or heterolytic cleavage in mass spec. So now you have the same molecule, the pi bond moves over here, and you have a positive over there. And this is going away as your methyl radical. Okay, and so this is 69, and this is 29, and so when you add them up, you would get 98. It's always the same in all cases. In this case, you have a methyl, and the methyl radical is 15. 15 and 83 gives you 98. So you can see in all of these cases, these two fragments should always match up with the molecular ion peak. The molecular ion peak obviously is the entire molecule, and that's always the first peak over here that you can see, and that typically may have a smaller tiny m+1 peak, but the m peak is the molecular ion peak. All right, so we have two of these. We have a 57 and 41 and 29. 29 is typically an ethyl, so this would be an ethyl cation. It's probably going to be something that we can see later on that you can cleave from here, and the 41. All right, so let's look at 57, which is basically, we saw 15 was methyl, 29 ethyl, 43 propyl, and 57 was butyl. Okay, so that's a 4-carbon fragment. Well, where can you get a 4-carbon fragment here? Well, it looks like this is a possibility. You have a 4-carbon piece that could come out. Let's work on that. Let's look at how that's possible. We can think of that as being C here. All right, let's see how that can be possible. In that case, let's say you take the same molecule, obviously it's the one that's traveling through the tube, and you hit it with an electron, and let's say you get a positive here and a radical here. And in this case, it's pretty simple. So here's a hydrogen. There's only one hydrogen because we started with a alkene. And so therefore, both of these can be pulled over, and you can get a cation here. So you will have a cation on your butyl part, and that'll be 57. This one was going to go over here, or you can think of it as making a double bond. And you can think of these two making a bond, and you can have a radical over here. Okay, so because that's going to fulfill the valence over here. 3 electrons altogether around that carbon. So that would be neutral. 1, 2, 3, 4. Formal charge is going to be 0. 1, 2, 3, 4, formal charge 0. So that's your 0 fragment, and that's your positive fragment that's going to hit the detector. So we got 98, 83, 69, and 57. 41, well, 43 is your propyl. So 2 hydrogens less would be 41. Well, how do you take 2 hydrogens off? Basically, when you make an alkene, you take 2 hydrogens off, so it's propene probably. And what are the ways in which you can make propene? So here again, here is your alkene, and you can think of the positive charge being on this side and not here. That's one possibility. Okay, let's call that D pathway. And again, it's the same thing over here. And you have a cation over here. And you have a radical over here. Okay, and you can think of this, then doing a homolytic cleavage and creating a cation on this side. So over here, you would have just 1 hydrogen, and so that's you can have a positive, but it's not going to be too stable, and you have a hydrogen here and a CH3 here. They should add up to 41. Z is equal to 1, so M over Z is 41. 69 is the most stable peak, and let's see why that could be the base peak, which means that set to 100, everything is measured relative to that. So for example, the molecular ion peak is about 1/5 the abundance of this, which means this is probably a lot more stable than this. So here, if you look at this, you have a pi and you have a positive ion, and you can have resonance. So you know resonance always makes the molecule more stable. So you can go back and forth and do resonance. So since it's a resonance stabilized cation, it probably can go through the machine without further fragmentation compared to other molecules. Its shelf life is a little bit longer. Let's look at the 29 peak here. What are the possibilities for 29? Well, 29 we know is an ethyl, so we got to take an ethyl group out of this molecule. Well, there are many ways to do this. This is one possibility. Here is your molecule again. Let's say you have a positive on this carbon. Remember, there is a alkene, so there's only one hydrogen here and one hydrogen here. And let's see, there is a radical over here. What are the possibilities? Well, here is a place where you can actually pull those electrons and make a double bond. So once you have a positive charge, it's a hole. It's looking for electrons to grab, and it's just going to grab this electron. So this piece is going to have to just fall off without those electrons, and therefore it's going to have a positive charge. It has hydrogens here and a CH3, and if you add that all up, that is going to be a cation, and that it's going to be 29 mass charge 1, so that's going to be m over z is 29, which didn't explain that. And all of the others are just going to go away as a neutral fragment. It's just going to go through the chute. Okay, and so radicals are neutral, and even anions are taken out. Most of the mass specs have just the cation fragments coming through the negatively charged plate and getting accelerated through that magnetic arc and falling according to their mass. This is one of the lowest masses here. There aren't too many lines. There aren't any lines, in fact, below this. All right, so I will see you soon, and we will talk about other molecules and possible pathways for other functional groups. So if ever you see an alkene, start with the double bond and see alpha cleavages. Those are the most common in mass specs. And then you can also account for all of the others through rearrangements and just simply breaking apart bonds. Talk to you soon, guys. Let me know if you have any questions. Bye.